sinks of biological in the atmosphere. Here are some of the sources of methane: permafrost, biological processes in wetland soils. Oil and gas reserves are a fairly substantial component of the methane cycle. But if you look over in the lower right-hand portion of the figure here, you see the ocean is a small component of the global methane cycle. But we know in Earth's past, there have been periods of time where methane played a very significant role in the global carbon cycle and contributed to climate change. So here's a little bit more about methane. It's a small molecule with a very big impact on climate. It has 30 times the warming potential of CO2 in the atmosphere over a 100-year time scale. And if we look at how methane concentrations increased and have increased over time since just 1980 shown here, there was a period of time where methane concentrations sort of seemed to stabilize, but then concentrations began to increase substantially again. And they're increasing today. One of the most temperature-sensitive reservoirs of methane is methane hydrates in the deep sea. This is a picture of a methane hydrate that we took with ROV Sebastian on a 2019 expedition. This hydrate mound is around 3.5 meters across and about 1.5 meters tall. And it's pretty typical for hydrates that you see in the deep sea. I'll show you some other pictures a bit later. But hydrates are really important because they concentrate methane 160 times relative to ambient concentrations in pore fluids. So hydrates, you can think of them as a sponge for methane. They suck it up and they concentrate it and they hold on to it as long as they're stable. The things that control hydrate stability are depth, temperature, and pressure. Pressure changes slightly with sea level rise. It's really not that significant in terms of hydrate stability. Temperature is the big factor that changes hydrate stability in the deep sea. So we've seen that methane emissions are low. I've told you that there are gigatons, probably around 2,500 to 5,000 gigatons of carbon stored in methane hydrate. So why are marine methane emissions so low? This is a question that I have chased throughout my career, and I think we're kind of getting close to figuring out why the emissions are so low, and I'll share that story with you today. So microbes in the ocean, very specific microbes that have a lot of special characteristics, are the primary sink for methane in the ocean. This is an image of an aerobic methanotrophic microorganism. And these organisms are special because of these stacked membranes inside their cells. Those membranes are where they concentrate the enzyme that they use to convert methane to they carry out the first step of methane oxidation, methane conversion to methanol in those stacked membrane lipids. These are methanotrophs that live in sediments. So we're not going to talk about them today, but they're important too. But it's these organisms that are sort of the last potential filter for methane out of the water column once it's been released from the sediment. So climate change may induce widespread gas hydrate dissociation. And if that happens, and we know that that's happening in some places already, like the Arctic and along shallow continental shelves in places like the Gulf of Mexico. When that happens, methane moves into the water column. And whether that methane is consumed or gets to the atmosphere depends on the activity of these methanotrophic organisms. One of the biggest challenges in marine biogeochemistry is trying to predict how these communities will respond to increased methane fluxes in their habitats. Right now, we don't know how they respond. So this is an image that shows some of these organisms that are responsible for methane oxidation. And I show you this simply because they're really spectacular organisms. They live in beautiful associations with other organisms. And we know a lot more about their evolutionary history, which is shown here, than we do about their functionality in the environment. So before I go further, I want to describe how we quantify rates of methane oxidation in the environment. Methane concentrations can be increased, like I said, from hydrate destabilization. But then once that methane gets to the water column, how do you figure out how much methane is being consumed so that you can then determine how much methane potentially gets to the atmosphere? Well, we do this with a radio tracer technique. So we use a tritium labeled methane molecule, and Hannah made this slide, so I want to give her a shout out for that. You add this is our kill control. So we kill this with formaldehyde, and then we have 3 live samples that get amended with this tritiated methane. It's the hydrogen that's labeled right here with tritiated hydrogen. We incubate the samples at in situ temperature and pressure. Once the samples have incubated for 24 to 48 hours, we basically, then we have a situation where some of that methane has been converted to water, okay? The carbon in the methane has been converted to CO2. The tritium molecules in the methane have been converted to water. We kill the samples with formaldehyde, so to halt activity, and then we take the samples and we purge them with hydrated air to remove the remaining methane tracer. This leaves us only with the tritiated water, and that is essentially easy to count on a liquid scintillation counter. And we can determine how much product there was, we know how much substrate we added, and from that we can calculate the rate. Okay, so this is essentially a summary of our work in the Gulf of California, and I'm going to give you the data to back this up over the course of the next few minutes. It's a spectacular geologic setting, and I can't help myself but to show some video of these locations, and I'll do that in a minute or two, because these habitats are really just mind-blowingly beautiful. I'm then going to show you data that will convince you that the Guaymas Basin in particular supports the highest rates of methane oxidation anywhere on Earth that's been measured in an aquatic system. And finally, I'll talk a little bit about the methanotrophic response and adaptation to hydrothermal inputs. So this is a map of the Gulf of California showing spreading centers and transform faults. They divide the system as you go from the mouth up to the headwaters. Carmen made this map. Our work has really focused on the Guaymas and Pescadero basins to date, but I'm really eager to go to the Carmen Basin and to some of the sites up in more shallow water near the headwaters of the system, because I think that could be a really interesting place to study methane dynamics as well. In the Guaymas Basin and throughout the Gulf of California, there's fluid circulation that's very similar to the kinds of fluid flow you see at mid-ocean ridges. Seawater migrates through cracks in the crust. It gets heated by magmatic sills, and then it moves through the system and is essentially discharged through the kinds of vents we saw on the first slide. And I'm going to show you another kind of vent in a couple of minutes. The other thing that happens in Guaymas that is really important is that this hydrothermal heating of sediments generates thermocatalytic methane. So it's essentially the same process that happens in the Gulf of Mexico over tens of millions of years to produce oil and gas in that system produces oil and gas in Guaymas on timescales less than 5,000 years. So this is essentially very geologically young oil and gas that's produced by in situ cracking of organic matter because of all this hydrothermal heat. And this is a slide that sort of shows that. There's enormous packages of sediment that overlie magmatic sills in the Gulf of California. And those sediments are generated by both in situ primary production, autochthonous primary production that's fueled by the rivers that bring nutrients into the system. And it's also fueled to some degree by upwelling. But this is a chlorophyll map showing the really high chlorophyll rates, concentrations in the water column. And this chlorophyll will, some of that material eventually sediments down to the seafloor. And that's what generates these thick sediment packages. And here's a magmatic sill heating these sediments and cracking the organic matter in them. So one of the reasons that I got interested in the Gulf of California, especially with respect to methane, is that I'm really a large part of the research effort in my group aims to understand how ocean systems are going to respond to climate change. And one of the big consequences of climate change, as I said previously, is the potential destabilization of methane hydrate deposits and this methane moving up into the ocean system. We know, because there are many, many paleo models of this sort of climate perturbation, large igneous provinces, these flood basalts, are present worldwide. And this is a map that just shows you the distribution of flood basalts. Flood basalts occur when magmatic intrusions come up through organic rich sediments generating CO2, methane, and sulfur oxides. And all of those gases can drive climate in different directions. The sulfur oxides are cooling, methane and CO2 are warming. I thought I'd just show some pictures of flood basalts. This is actually a flood basalt province in the Hidalgo area in Mexico. This is a picture that a student of mine took when we were visiting Devil's Postpile in Yosemite National Park a few years back. And this is a picture of a flood basalt in Panama that one of my former graduate students who is from Colombia took. So the relevance of this is that when these flood basalts migrate through either gassy or oil and gas rich sedimentary deposits, it mobilizes carbon that can then go up into the atmosphere and impact climate. Does that sound familiar? That's exactly what's happening in the Gulf of California today. So these volcanic sill intrusions into organic rich rocks essentially destabilize carbon pools and move methane, sulfur aerosols, and CO2 into the atmosphere. And in some cases, that material is released into the ocean. And when it is released into the oceans, oceanic methanotrophs have a shot at consuming that methane. There's really strong geologic evidence that these volcanic sill intrusions have played a major role in past climate events, especially here at the PT boundary extinction event and associated with the Cretaceous Tertiary boundary event. But it's potentially possible that they played bigger roles in other events as well. So the question that we really have been trying to answer is, the Gulf of California is a modern analog for these large igneous provinces. So how is this system going to respond to, I'm going to get rid of this video panel. Ta-da. I didn't notice it was blocking your view over there. Sorry about that. But how do these pelagic systems respond to large inputs of methane from sedimentary discharge? So before I show you the video that I've mentioned 4 times already, I think this is my favorite video that we've ever shot. Carmen was out there when we shot this video. It's pretty amazing. But sampling hydrothermal plumes is hard, okay? if you're in a human occupied vehicle, the pilot doesn't want you to get really close to a hydrothermal plume because they're really hot and the windows are rated to 40 degrees and these discharging fluids are 300 plus degrees centigrade. So it's really hard to get close with a human occupied vehicle. It's even hard to get close with a ROV because they still don't want you to melt components of the vehicle. So the way that we can sample, 10 meters or so, 5 meters if you're lucky and you have a pilot that is willing to be a bit of a daredevil, you can get about 5 meters above the bottom. With the CTD rosette, you have to be exceedingly patient. But if you're patient and you take your time, you can basically wiggle your way over and position the rosette in the hydrothermal plume. And we do this by having an acoustic transponder on the rosette, and we run the multi-beam system, the sonar system at the same time, and we can see the rosette and we can see the plume, and we put the two together. And then we can get really, really great samples of plumes. And how do we know? We can measure large temperature anomalies in the CTD. So this is the Big Pagoda vent. And when we first visited this site in 2019, we sat there for a long time. I don't remember how long, and nobody said a word because we were just stunned. We'd never seen anything discharging like that. Most of the hydrothermal vents in the Gulf of California look like this. They're still impressive, but most of them aren't like that, right? This is an exceedingly productive feature. And this is where I'm going to start with Big Pagoda because it's the most intense plume that we captured during our study. So this is the location of Big Pagoda here, and you've seen a picture of the back side of Big Pagoda. This is the front side of Big Pagoda. Multiple flanges discharging fluid contemporaneously, and all of that fluid generates one very large plume that moves away from the structure. I'm only going to show you the bottom 200 meters or so of these profiles because the rates of methane oxidation above about 1,800 meters are pretty low. But you can see here the temperature anomaly that we measured in the Big Pagoda plume. It was around 2 degrees. And here's radium-224. This is a tracer molecule that we use to track hydrothermal discharge. So we don't always get congruency 100% between the highest radium and the highest temperature. That's because these plumes are moving and mixing as they rise to reach neutral buoyancy. But you can see that we basically got a pretty good hit on this cast. The blue line here is the methane oxidation rate, and the red line in this panel is the methane concentration. The methane concentrations in this cast were around 420 micromolar. For your comparison, water in equilibrium with the atmosphere is 4 nanomolar methane. So this is 6 orders of magnitude higher than what you would expect from atmospheric equilibrium. And the rates of methane oxidation that we measured are about the highest that have ever been measured anywhere. And I'm going to summarize that for you in just a second. This is, again, Hannah's work. This is a paper that's in review right now, and we're hoping to hear a positive decision on its publication soon. So these are all the data from the Gulf of California that we collected on that 2019 cruise. It's over 700 data points, I think. And the 2 highest rates that we measured were both from Big Pagoda, 20.9 micromoles per liter per day and 30.9 micromoles per liter per day. And again, as you might expect, the rates of methane oxidation in the surface ocean where methane concentrations are low are about their picomolar per day. So again, about 6 orders of magnitude lower than what we see in the plumes. This is a site on the Sonora margin, this hydrate site that I showed the picture of earlier. And here's a close-up of that hydrate again. And along Sonora margin, there's no hydrothermalism active right now, but there's a lot of oil and gas seepage. And we see no temperature anomaly because there's no venting, and no radium anomaly because, again, there's very little, there's no discharge of hydrothermal fluids. We do see radium anomalies at cold seeps occasionally, but you can see a little blip right here if you stare at it long enough. But it's not nearly the kind of anomaly that you see at hydrothermal vents. And the methane concentration and rate of oxidation shown here, again, they increase as you go down towards the seafloor where the cold fluids are seeping out. But the rates are much, much lower than we saw at Big Pagoda, as are the concentrations. The highest concentration at this site was 80 nanomolar, and the methane oxidation rate was nanomolar per day instead of micromolar per day. We also sampled in the Pescadero Basin at Z-Vent. This is a picture from Z-Vent that we took on a recent expedition in April of this year. And Z-Vent was really interesting because it had the highest radium concentrations that we measured anywhere. And we got an enormous temperature anomaly. This is 3,800 meters water depth. The fact that we can catch a plume, I was doing backflips on the deck this day because I was not sure that we would be able to capture a plume at this depth. But we obviously mastered the art in the 3 weeks leading up to this collection, and we got really good samples at Z-Vent. Again, the rates are really high, but surprisingly, the concentrations weren't as high as Big Pagoda, and the rates weren't as high as Big Pagoda. So Guaymas rates are higher than rates in Pescadero, despite a lot of input of hydrothermal fluid, as far as the radium tells us. And I'm only going to show you a single profile from each location for the sake of time. But believe me when I tell you that all of the rates we have in Guaymas Basin are higher than the rates we typically see in Pescadero. Guaymas is just special. And I think we know why that is. I'll show you that in a few minutes. So this is the vertical profiles for methane concentration and methane turnover time in days for Big Pagoda in red, Pescadero in yellow, Sonora margin in blue, and the control site, which is an off-seep, off-vent control area in the satellite basin in this grayish color. And you can see that even in the off-site area, the turnover constant's around 21 days. And this turnover constant, what does it tell us? It tells us how fast that population is processing methane. And the fact that we've got really rapid turnover at essentially a control site tells us something about how water in the basin is circulating, and that essentially there's so much inputs in the southern part of the trough and in some places in the northern graben as well, that the entire area is primed for high rates of methane oxidation. And this is just another way to look at this. This is methane concentration, oxidation rate. And what I've shown here, this is the only biology slide I'm going to show. This is the hits of the gene that is the first step in methane oxidation. So this basically tells you if the population of methanotrophs, how it varies over depth. And what you can see is that the population it's increasing with depth as you basically as the turnover time changes. And that means the population is responding to the methane inputs locally. So we made a little schematic to describe how this works in theory. And here's the hydrothermal vent. Here's the plume. This is near end member fluid, so the highest concentrations. The rising plume is diluted constantly, so the methane concentrations are decreasing. And then as you get up to this dilute plume, you've got really low concentrations of methane relative to down here, but still elevated relative to what you would see, say, at a background site, outside the Gulf of California. The turnover time is actually maximal in here in this rising plume. So the population has had a time to, it's had time to grow in, and it's turning over methane rapidly. But the methane oxidation rate tracks methane concentration, and it's highest down here where the methane concentrations are highest. I mentioned before that there was something special about the Guaymas Basin, and that is that there's a sill about 200 meters water depth that separates the water inside the Guaymas Basin from the water outside the Guaymas Basin. And on our recent cruise, when we sampled at a lot of places inside Guaymas, even places pretty far away from areas of discharge had consistently low turnover times, so that it's turning over methane really fast. And it looks like the water below the sill depth is functioning as what we would call in biology a chemostat, or a reactor. And that methane is getting consumed very effectively because the population is trapped in there and it has contact with methane frequently. And you can see that if you look at the turnover time. So this is near the bottom, this is below the sill depth, and this is above the sill depth. And the average turnover time is substantially higher above that sill depth compared to below the sill depth and right at the vent. So to summarize this part of the talk, Guaymas Basin hydrothermal fluid methane concentrations are extremely high. The end-member concentrations are on the order of 100 millimoles per kilogram of fluid that's discharged. So the end-member fluid concentrations, close to that source at high temperature, are around 85 to 90 millimolar methane. So really high methane concentrations. We think that methane concentrations now are higher than they were in the late 1980s when the concentrations were determined for the first time. And that's probably because we have better methods of collecting those end-member fluids now than they did in 1988. Despite these high concentrations, the microbial community is able to turn over this methane on the order of weeks, faster than anywhere else that's been observed so far. This was really surprising to us when we first discovered this. We think that the microbial community is able to respond to methane injection on the timescale of the rising plume, which is hours. And when you think like a microbe, which I do a lot, microbes don't turn things over that fast usually, unless you're living in a chemostat. You don't turn things over very fast. They're living in a chemostat in Guaymas, and that's why they can turn things over so fast. But the other reason that these microbes are very happy is that there are inorganic nutrients, nitrogen and phosphorus, and all kinds of metals, from copper to cobalt to nickel, coming out with these hydrothermal fluids. So these are probably the happiest methanotrophs in the world that live in the Gulf of California, because they have everything that they need to thrive. Most places are not like that. So they're prepared for high methane oxidation and high, substantial for methanotrophy because they're always exposed to methane, and they may be in moderately high methane today and a little bit lower tomorrow. And then the next day after that, it'll be really high, but they get a constant dose of methane, which keeps that population primed. So the question is, how does Guaymas compare to other methane-rich systems? Like, is it a fluke? Is it the only place where you see anything like this? Or is it teaching us something fundamental about how these populations respond? And to talk about that a little bit, I want to talk about the Deepwater Horizon oil well blowout that happened in 2010 in the Gulf of Mexico. This turned out to be a really interesting accidental experiment. It was a large-scale injection of 250,000 metric tons of methane into the deep water. And we were, I don't know if we were fortunate or unfortunate, but we were the first people out there after the oil spill We got out around 10 days after the incident began. And then we had 6 cruises over the next 7 months. We were at sea for a total of 6.5 months, over 10 months in my group. I mean, me and Melitza and a couple of other people lived on the boat in 2010. It was hard, but what we were able to do was generate a really unprecedented time series of the response of the Gulf system to this methane infusion. And I'm going to show you a couple of slides that describe the response of this community to this methane injection. And they are all color-coded like this one. So this slide shows where we sampled when. So the blue colors are essentially the first 60 days of the incident. Then it goes to light blue and yellow for 100 to 150 days. And then 200 plus days are the reddish colors, which we sampled close to the wellhead on that. We went back to see if the rates were still elevated there. And we went over here because the NOAA models had proposed that all that methane was getting washed out to the west, which I don't believe, but that was what the model said. So we went over there to look for methane, and we didn't really find any over there. So the Guaymas data set that we generated for methane oxidation rates is the second biggest data set that we've ever generated. This is the first biggest data set. This is, I don't know that this will ever, I hope this is never beaten. I hope it's only one of a kind. But what you can see here, there are 2 things that are important. So one, there are some points that have error bars on them. These guys right here. These are data points that were generated by Dave Valentine at UC Santa Barbara on his cruise in mid-June to early July 2010. These are our points from early May, late May, and early July. And what I want you to notice is that our data and his data align very well. We don't, I mean, the reason that our points are higher out here is because we're out there earlier than they were, and the concentrations were higher at that point. And once this lateral plume was not a lateral plume for very long, because the Gulf of Mexico bottom is not flat. You all know that probably. There's tremendous amount of topography from the salt tectonics in that system. And when the water moves along a surface that has seamounts and hills and mounds and all kinds of variability, that generates mixing in the water column. And that piston velocity that's generated by the water moving across a bottom with a lot of topography mixes the water column very effectively. And this is a physical mixing phenomenon. And we had worked with a physical oceanographer who developed an incredibly fine-tuned model and was able to basically drop microorganisms and methane into this plume, in her computer. And she showed convincingly that it took less than 100 days to basically smear that plume all across the water column. And that's exactly what we saw in the data. It smeared in about 100 days. So you had really high rates in this plume. And there were some places early on where we got low rates, but that was up high in the water column, not right here. And you'll also notice that the high rates are not down near the bottom, because this plume came up, it reached neutral buoyancy, and it moved west. So, and it was like a snake. I mean, every time we went, we never went to a place twice and got the same data because the water was moving and mixing. It was incredibly dynamic. But these rates, the highest concentration that we measured during Deepwater Horizon, 375 micromolar, comparable to Guaymas plumes. But this was a one-time input. Well, not a one-time for 87 days, but an 87-day long input that then stopped. And once you stop that input, the plume was smeared. If we look at rates, the rates are also highest early on in the spill. And you can really see with Dave's measurements here, his rates were substantially lower than ours by several orders of magnitude because he was out there later than we were. So in the beginning, everybody was like, oh, your data doesn't match. Well, of course it doesn't match. It matches when you put them on the same time scale, because, you know, the rates that we measured in this period are very well aligned with their rates, but our early rates are really high. So our maximum rate that we measured was 6 micromoles per liter per day. So that's about a quarter of what the highest rate in Guaymas, you know, maybe 20% of that 30 micromolar rate that we measured in Guaymas. So the interesting thing about this was, you know, the concentrations increased by 100,000-fold. The rates increased by 1,000,000-fold, by 6 orders of magnitude. And methanotrophic activity took 3 weeks to reach maximal rates once it was exposed to high methane. That's not like Guaymas. In Guaymas, you expose that community to methane, the rate ramps right up. We've done this in the lab. We've taken, you know, samples from 300 meters, added methane, let them sit for a week, and the rates are really high. That's not what we saw during deep water. It took 3 weeks for rates to ramp up. Rates peaked at 5 weeks. And so the high activity wasn't sustained. It crashed after that. And was it solely because the concentration crashed? I don't think so. I think it's a little bit more complicated than that. And I think I lied. I said I only had one biological. This is kind of another biological slide. Sorry. So what limited methane oxidation in this system? So here's the pre-discharge scenario. You can tell I'm not an artist either. This is the pre-discharge scenario: low biomass of methanotrophs, low concentrations of methane. Then you had the discharge. And what happened at 5 weeks, you had over 100 micromolar methane still, and you had 100 times the abundance of methanotrophs relative to baseline, and the rates were micromolar per day. So between 5 and 8 weeks, the rate crashed. And I scratched my head about this for months, and until we had, you know, the longer term data set. And then it became clear that it was 2 things. One was that the organisms that responded between this time point was a high methane community. It was a community that was tuned to respond to really high methane concentrations. It needed high methane concentrations to survive. When that methane concentration dropped, it was below the half saturation constant. So essentially, you can think about it as, you know, if there was a donut every 10 feet throughout this hotel, your chances of getting a donut are pretty good. But if there's one donut hidden on one floor of the hotel, you would have to wander around for days to find that donut. You would be starved to death by the time you find the donut. And that's what happened to these methanotrophs. They basically had more food that they knew what to do with, and they were able to really just go to town. And then when the methane dropped, they couldn't do anything. And these guys had all consumed all the nutrients and all the metals. There was nothing for the other guys to grow off of, so the methane oxidation rate crashed. So what we learned from this is that microbial methanotrophy is not infinitely scalable in most parts of the ocean. We have a really poor understanding of the factors that control community structure in these organisms. And we know that organisms that are tuned to high concentrations can do well when there's high concentrations, but that pretty much eliminates the possibility of any other organism responding and doing well, because they eat up everything and there's nothing left for anybody else. And this methane exposure time really seems to be the key to the whole story. So I'm going to wrap up over the next 2 minutes, and I want to spend a few minutes talking about future climate change, because I think this is really important. Methane hydrates occur at water depths greater than 500 meters, right? And the temperature at 500 meters along that isobath is typically around 8 degrees centigrade, okay? We've all heard about surface ocean heat waves. How many people have heard about deep ocean heat waves? That is a thing. This is model output, because there's very little monitoring data in the deep sea, which is a big problem. But this is model data that predicts the sensitivity of a given area, the propensity for an area to be impacted by deep ocean heat waves. If you look at the Gulf of Mexico here, you will see that it's essentially that red color. This is the depths where the heat waves hit. So this is, greater than 600 meters. It's got 100% propensity of being exposed to a deep ocean heat wave at least once a year. If a hydrate's exposed to temperatures above the stability horizon for more than 2 days, it starts to sublime. So we've had thermistors out in the Gulf of Mexico, and when a storm moves through the shallow sites, from 500 to 1,000 meters, between 7 days and 18 days, the temperature can be up to 4 degrees centigrade higher than normal. So 8 degrees Fahrenheit higher. That's plenty to destabilize hydrates. This is another hydrate from a site we call birthday candles. These are asphaltene chimneys, little fingers, cigar chimneys is what Ian McDonald, my colleague, calls them. These sorts of hydrates are all over the Gulf of Mexico. The hydrates there aren't clean like they are in the Gulf of California. They're basically saturated with oil. So if you have stochastic methane release from hydrates, that's not going to be sufficient to promote growth of methanotrophs. I just showed you data from the Gulf of Mexico. It took 3 weeks of exposure to high methane for those communities to begin to ramp up, and then it was 2 more weeks before the activity was maximal. So stochastic inputs aren't going to be enough to tune a population to act like Guaymas. Guaymas is special because those high inputs happen all the time. These short-term pulses of methane are unlikely to be consumed efficiently. And that means that the methane biofilter is inefficient. And it's inefficient because the constraints on methanotrophic growth, nutrients and metals probably play a role here too. It's really unclear if these communities are going to be able to adapt to higher methane concentrations under the conditions that we expect these higher methane concentrations to occur. And it would be one thing if hydrates sort of gradually destabilize, but most of the models don't show gradual destabilization. They show pulses of destabilization as the conditions permit, so with high temperatures or what have you. So I think we are in a pretty good place now where we can say that it's very likely that a substantial portion of, if hydrates destabilize, barring some unforeseen circumstance, it's going to be hard for methanotrophs to respond to that methane injection. But we can learn a lot from Guaymas. And by studying the physiology of these methanotrophs, which we're doing using samples from our most recent cruise, we're hoping that we can figure out some sort of a special mechanism that we can use to help these methanotrophs from cold seep sites begin to act more like the methanotrophs from around the hydrothermal vents in Guaymas. So with that, I want to thank you for your attention, and I'm happy to answer any questions you might have.
Bueno, sí, acá.
Can you translate for me if I'm confused? Thank you.
Very nice talk.
Thank you.
Thank you very much. I'm a physical oceanographer working in the Gulf of Mexico. And I do wonder, I mean, what do you think about natural oil seeps in the Gulf of Mexico? Because you ascribe these a lot of, single events, but
Oh, there's natural seepage all the time. So we had this idea after the oil spill. We had a 10-year project to study natural seeps in the Gulf of Mexico. And we had this idea that, oh, it is translating. Okay. We had this idea that the natural seeps formed a priming function like the vents in Guaymas. But what we discovered is that, you know, these natural seeps, they create circulation cells just like you get at hydrothermal vents, but they're too far apart to generate the kind of dynamic you see in Guaymas. And one of my former postdocs did an experiment that one day she will publish, where she did this exposure test and with water from all over the place in the Gulf of Mexico, Green Canyon, Alaminos Canyon, Mississippi Canyon, all over the place. And what she saw was this 21-day magic period of ramp that is consistent. None of these communities respond fast. They all respond slow. And I think it's because there's just not a lot of I mean, the seepage is persistent, but it's also incredibly stochastic. We've had cameras on seeps in the Gulf of Mexico, and it'll be blowing oil and gas out for 3 days, and then it stops. And then it blows oil and gas out, and then it stops. And that stochasticity is the problem. But it's also the reason the oil degraders can consume the oil. Because if you had a constant barrage of oil getting into the system, you would overwhelm the oil degraders, because they don't ever seem to get fast. They're just perpetually slow. They're the tortoise in the game, and the methanotrophs are the hare if they get enough exposure to methane.
Well, I do have another one, if I
Yeah.
may. You know, we have been insisting, you know, and in this meeting, our seismology colleagues who do exploration for oil actually, and we are very interested in the data they get in the ocean, which they normally throw away.
Oh, yeah.
And I do wonder, you know, it's 1 hertz kind of sampling for getting, well, deep into the bottom, ocean bottom. But for the ocean, you can actually see a lot of temperature gradients and a lot of structure. And I do wonder if you have ever seen this kind of data and whether you would see these signals there.
So those data exist. I have tried for
Oh,
7 years
You
to
are one
get
of
them.
us.
Oh my gosh. I mean, I don't know what it takes. It probably takes a presidential decree to get that data. I really don't know, because we've tried in the Gulf of Mexico with, I think, every oil company. Nobody wants to share it. And, you know, we even have colleagues that we work with in the industry, and they're like, that would be really cool to look at that, because I mean, imagine if we could see, I predict there's an increase in frequency of deep water heat waves, especially in the last decade. I would really like to be able to prove that. Our record that we had was for 2017. I was out in the Gulf with the BBC filming for Blue Planet 2 in 2016, and they really wanted to film hydrates. We went everywhere. It was so hot. I thought the temperature sensors on their CTDs on the subs were broken. We took those sensors off several times and recalibrated them. They were never broken. It was 14 degrees C in the bottom instead of 8. And there was no hydrate anywhere. But you know what we saw? Tons of dead tube worms. I mean, there had been just hydrate blowouts, and there was silt all over all these animals, mussel beds dead, tube worms dead. So clearly the hydrates had destabilized and killed all these animals. So we went back out. That was in June. We went back out in August, and we put these temperature sensors at 4 different sites. And we only had like 5 that weren't deployed on landers, but we had 4 sites. One of them had 2 sensors. And we got that record back about a year later, and there were 9 periods of more than 5 days of temperatures exceeding hydrate stability. And the deepest one that we had was at 1,200 meters, and there was a lag, you know, going deeper, but you saw temperature increases at 1,200 meters. It wasn't that. It was only 2 degrees instead of, but that's enough to destabilize hydrate. I mean, these weren't hurricanes. These were like little wimpy storms moving through there that were driving temperatures like that. We had one deployment with a lander where we saw a hurricane come across, and that was, I think, a 7.5 degree ramp up.
No, I was just going to ask you again if you could explain what the destabilization is. Just basically, is it like that you're gonna not be able to hold the methane in the water because of the temperature going up? Because I missed that. Okay. So that's what it is.
So the hydrates are, you can grow hydrates in the lab in a pressure vessel. And so you keep the pressure stable and you crank the temperature up, and you can see really precisely when the hydrates start to destabilize. And it's about a half a degree to a degree centigrade that is required for the hydrates to destabilize. So if you just have warm water flow past the hydrate mound for a day, it may not destabilize. A lot of them are covered with sediment. You know, the temperature has to propagate through the sediment. We did this one project where we drilled holes in hydrate and put thermistor strings in the hydrate down to like 6, I think it was 6 inches. And you're basically calculating the heating capacity of the hydrate, and they warmed up within, you know, if you had a big storm event move through, you could get heat propagated all the way down to the bottom of the hole. And so I know this happens. I mean, I've seen it firsthand. I mean, we spent a month looking for hydrates in 2016 and didn't see any. So it definitely happens. And we've seen instances where we show up, it's, you know, been super hot and the seepage is just really intense. But we can't say whether that's because hydrates destabilize. We just know that when we showed up, seepage was really intense. So we've had cameras out there, you know, when we had thermistors on landers, and we can correlate like the bubble flux and the temperature. And there is a positive correlation between bubble flux and temperature. And that to me screams hydrate destabilization. It's one of these things that is hard to study because you need a lot of really expensive instrumentation to do it. And you need to go out to sea every 3 months for a year or two. I mean, Carlos and Carmen and I have a proposal to do this in the Gulf of Mexico. And it's going to go back in February because I think it's critically important. Think about climate models. Climate models don't consider methane climate models consider the ocean to be a trivial source of methane, and it's really efficient methane sink, but it isn't really.
Thanks very much for this interesting and very nice talk. My question is about climate and the effect of methane. And I was wondering about that. What could you tell us about the effect of methane in climate? And essentially, if it is these sources very important or not?
Sure.
And of course, we would like to know as a whole if the ocean is receiving or it is a source of methane, and of course there will be spatial variability.
Yeah.
What's your opinion?
So if you look at paleoclimate data sets, and especially data sets that have proxies for methane and CO2, and you look at sort of the onset of rapid temperature rise, methane is frequently the first to shoot up. It often precedes CO2 in increasing. And that says to me that there's got to be a source in the biosphere, whether it's on land or in the ocean, that is injecting a bunch of methane into the atmosphere. There has been an ongoing argument for at least 20 years on whether this is hydrates or permafrost. And, the isotopic signature of oceanic thermogenic methane in the ocean and permafrost methane. So hydrates with thermogenic methane like the Gulf of Mexico versus permafrost with that methane is around -45. Hydrate methane from the Gulf of Mexico, -45. You can't distinguish those two sources that way. So there are a number of really reputable scientists who are convinced that the Arctic is a really important source of that rapid amplification and rapid methane release. I think they're absolutely right, but it doesn't have to. It probably isn't one source. There can be other sources, and these continental margin hydrates, there are a lot of them the minimum estimate is 2,500 gigatons. The high end is around 7,500 gigatons. That's a huge range. And we can't really afford to be wrong about that. About half of that is considered really temperature, it can be destabilized by temperature increases. So there's a lot of methane that is prone to temperature-driven destabilization. The question then becomes, well, how does the ocean respond? And no one has ever published a paper showing rapid response of methanotrophs in the ocean. It just doesn't exist. It's not there. That's not how they behave, because they're, I hate to anthropomorphize microbes, but they are really wimpy. They would lose the race every time if they were in a race with other microbes. They have a lot of special nutritional requirements that makes it hard for them to grow rapidly in the ocean. It's why they grow so well in Guaymas, because there's nitrogen and phosphorus and metals coming in with the hydrothermal fluid. You don't see that in the Gulf of Mexico. Iron was drawn down to 0 in the deepwater plume by methanotrophs growing. So you just don't see that. So I think, I have had proposals where we worked with climate modelers and we wanted to incorporate methane into climate models, because right now it's not integrated into climate models in any way that is remotely sufficient. It's really bad. And, we haven't gotten funded to do it, but it needs to be done. So we have another proposal that we're putting in November to do that. But there's another side of this that I didn't talk about, but I think it is important. So I'm going to mention it. So we've been talking about the bottom of the ocean and methane coming from the bottom of the ocean. There's actually a really important source of methane in the mixed layer. It was only discovered about 15 years ago, and it's a suite of processes that are all microbially mediated. And essentially the short version is that when phytoplankton and bacteria are nutrient limited in the surface ocean, they will reductively demethylate. And that sounds complicated, but it isn't. Imagine you have a methylated amine. So you have a methyl group with an amine group over here. There are microbes that basically chop this in half. They release the methane and they eat the nitrogen. They could do the same thing with methylphosphonates to get phosphorus. They can do the same thing with methyl sulfides to get sulfur. And then there's a whole nother suite of processes that are actually oxidative. And they involve Fenton chemistry, which simply put, if you've got low level iron and oxygen radicals, you can make methane from anything. And this happens in trees, it happens in the ocean, it happens in human tissue, in a dish in the lab. It's crazy, but it happens everywhere. But this mixed layer methane, I think, is the elephant in the room that nobody is talking about. Because what happens as the ocean warms? They become more stratified, right? And if the oceans become more stratified, what happens? They're more nutrient limited. And if they're more nutrient limited, what happens? You got more methane production in the mixed layer. And that's the mixed layer. That's shooting right out of the top. That's not going to get consumed. I mean, Hannah, one chapter in Hannah's thesis is about this cryptic methane cycle in the surface ocean. And I didn't have time to talk about that today. And she did most of that work on the East Coast. Gulf of California is pretty nutrient rich. It's not really, we tried to measure it there in April. We didn't see anything. But on the East Coast and in the Gulf of Mexico, this is really important. And one of the reasons that I realized how important it was that these turnover times for methane in the surface mixed layer are as high as they are right above a seep. So there's clearly a huge methane source in the mixed layer. The two processes aren't balanced. There's more production than there is oxidation, but there's still a lot more oxidation than there should be based on the fact that, it's the mixed layer of the ocean and it's mixed, it's ventilated. So this process to me, that keeps me up at night as much as hydrates do, because there's a whole lot of ocean that is nutrient limited. And goodness gracious, the methane production rates in the mixed layer are as high as they are in some sediments, which is crazy. That's just crazy, but it's true. And so I think both of these things, climate change and methane, if there are any students out there, I'm always looking for students to work on this, because only one student can do one, you can only work in one place. So I have like 4 places we're doing this and I need 2 more people. So hit me up.
Se acerquen por cualquier colaboración o pregunta. Muchas gracias. Thank you.
Sure, thank you. I wanted to introduce you.